Okay, I think people are joining still, but we could probably slowly start. Hi, everyone. I'd like to welcome you all to the 31st webinar in this discussion series on tipping elements, the notion of irreversibility and abrupt changes in the Earth system. My name is Annika Hübner. I have worked on tipping risk assessments at PIC and am currently a doctoral researcher at the EASA, and I will be moderating the webinar today. I think we still have more people joining. That's fantastic. The goal of this discussion series is to advance knowledge on tipping elements, support efforts to increase consistency in treatment of tipping elements in the scientific community, to develop a research agenda and design joint experiments and ideas for a tipping point modeling intercomparison project. And the networks behind this series are the Earth Commission, AIMS, the Analysis, Integration and Modeling of the Earth System project. Both AIMS and the Earth Commission are hosted by Future Earth. Then the Safe Landing Climate's Lighthouse activity of the World Climate Research Program. And this event is co-organized by the International Institute for Applied Systems Analysis, the Potsdam Institute for Climate Impact Research, and the Global Systems Institute at the University of Exeter. Many thanks also to the organizers. Very briefly on the house rules, it's basically just one that you need to know. If you have questions, please drop them in the Q&A box, not in the chat. So in the Q&A box, we're collecting your questions, and then we can get to them in the discussion part. The focus for today is on AMOC shifts, scientific insights and policy implications. Both of our speakers will be present for the Q&A session. So you can already collect your questions during their talks using the Q&A feature. It's here at the bottom of the Zoom window. I hope you can see it. Please indicate to who your question is directed. And there's also the option within the Q&A box that you can upvote questions that you find particularly interesting. We will then get to these questions in the discussion session following the presentations. In a few days, the recording will be posted and the slides made available on the Tipping Point Series Confetti webpage, so they will be accessible for you also in the future. All right. Cool, then let's begin. Our first speaker today is Maya Ben-Yami. Maya Ben-Yami is a doctoral researcher in the Critical Earth Age 2020 Innovative Training Network, working at the Technical University of Munich and the Potsdam Institute of Climate Impact Research. Her work focuses on the Atlantic Meridional Overturning Circulation, the AMOC, using a combination of real-world and model data to understand this complex system. In particular, she investigates the impacts of a potential AMOC collapse on the global climate and works to find robust early warning signals for a future AMOC tipping. Thank you, Maya, for joining us today. I hand over to you.
Yeah, thank you for that introduction. Okay, so I'll share my slides. There we go. Okay, you can see everything properly? Great. Yeah, so welcome everyone. In the first part of this webinar, I'll be talking about basically the climate impacts of an AMOC collapse. And obviously in 20 minutes, I can't, talk about all the effects that AMOC collapse would have. Instead, I want to give you an overview and then also maybe a little insight through two examples into the sort of nuances of, how AMOC impacts are more complicated than just a sort of like big annual mean picture, and why we sort of need more research into them. So yeah, to start, I'll give a little bit of introduction and then we'll go into the impact and complexity. So for those of you that need a refresher on this topic, the AMOC, like Annika said, stands for Atlantic Meridional Overturning Circulation, and you can see a rough sketch of it here in this figure. Let me get my laser pointer. So you have these sort of like red currents, there's sort of these warm surface currents going from the south to the north across the Atlantic. Then in the north, the water gets colder, but it's also salty coming from the south. So it's dense and sinks down. We call that process deep water formation. And then you have these blue, deep, cold, dense currents coming back south in the Atlantic. And this sort of like the important thing for today about this overall circulation is that it transports heat from the south to the north across the Atlantic basin. And so the reason that we're here talking about the AMOC at all is that in the future with global warming, because the sort of northern part of the Atlantic Ocean warms, and there's also sort of more rain and melting ice from sea ice and ice sheets, basically that sort of both heats the waters in the North Atlantic and also makes them fresher, which makes the water sort of like lighter, less dense, and so you have less deep water formation. And there's a reduction in this force that is causing, basically helping drive the AMOC through this sinking in the North Atlantic. And so also when we look at what climate model experiments tell us, right, these sort of like models where you divide the Earth into lots of little squares and parameterize the physics, when we sort of project into the future with different emission scenarios, red being worse than blue, you can see that this is sort of a few picked scenarios where basically if you project past 2100 into the future, you see that the AMOC actually collapses. It goes down to a very small number. And here at the start of this presentation, I want to make a little bit of a terminology slide, because of course we're sitting here in the tipping points discussion series because the AMOC is suspected to be a potential tipping element, which means that this sort of collapse that we see could be a transition to an alternative state where actually if you reverse the warming, it might not, go back to its strong state. But in this presentation, I'm not going to be making a distinction between tipping or not tipping, because sort of in terms of impact, all that matters is that it's a collapse. So it's a reduction to this very small strength, basically. There's a few ways, there's not an exact definition, but you can see that here the AMOC goes from sort of strong to below 5 stradrops in strength. So now we get to like what actually happens when the AMOC sort of like weakens this much, when it's sort of the circulation goes away. Well, the way that we sort of find out about this, we have a lot of different ways, but in this presentation, I'll mostly be talking about impacts from sort of like climate model experiments where you use freshwater hosing. This is sort of a schematic of what's happening, that in this area of the North Atlantic, you basically change numbers in the model so that you're getting like extra fresh water coming in. And so in this simulation, as an example, you start from a sort of strong control AMOC, and then you add this hosing, and the AMOC weakens. This is really useful because it isolates just the impact of an AMOC collapse, right? We have nothing else interfering, it's just that. But again, something to keep in mind when you see the results I'm presenting today is that these impacts may be slightly different if they're combined with global warming, right? So in this scenario, as I was sort of showing before, the impacts here may be a little bit different because you also have, something like 4 degrees of warming, which also impacts the climate in a different way. But when we look at what happens just if we turn off the AMOC without anything else, basically this heat transport that I was talking about, that the AMOC transports from south to north, this weakens. And so in sort of like overall, you get a colder northern hemisphere, especially in the Atlantic Ocean, and a little bit of a warmer southern hemisphere. And you can see this here in these model results from the HGM model, which I also showed you the experiment before, where basically you see this sort of like widespread northern hemisphere cooling and a little bit warming in the south. And the cooling is a bit more over the Atlantic Ocean, but it is over most of the hemisphere. And so as we know from, everything we know about climate change, like changes in temperature in the climate aren't just changes in temperature, right? Like you change temperature in the climate and you affect everything else. And the really important thing for understanding the AMOC impact is understanding that you sort of have these tropical precipitation belt. So here I write ITCZ, it's the Intertropical Convergence Zone. There's a few different ways to think of it or define it. Basically, it's this belt of converging trade winds and rising air near the equator. And here, the reason I have this sea surface temperature map is because the way I like to think in connection to the AMOC about the ITCZ is that basically you have this rising air and precipitation over the warmest sea surface temperatures. It's a bit more complicated over the land, but over the ocean, it's that. And then basically when your warmest area of sea surface temperatures moves, the ITCZ belt, the location of the rainfall, moves with it. And you can see that quite well here on this animation, which is observations actually of the Earth in 1 year, sort of like on the top left, you see the sea surface temperatures. On the bottom right, the monthly precipitation. And you can clearly see this intense band of precipitation in the tropics moving sort of south to north, basically following the area of warmest sea surface temperatures here, as you can see moving on the top. And you can already imagine that if, we get an AMOC collapse and we have sort of like cooling of the whole northern hemisphere, the area of warmest sea surface temperatures is going to move to the south. And so this rainfall belt moves to the south. This is here the annual mean precipitation anomaly. Green is more rain, brown is less. And you can clearly see around the equator, this sort of like extra sort of rain to the south, less to the north. Basically, this whole belt is sort of moving to the south. So yeah, these are their overall impacts, quite clear, cooling in the northern hemisphere, southward shift of the tropical precipitation belt. But sometimes when you look at just the overall impacts, you don't get quite the clear picture. So because we're also going to have Laurie later talking about, more economical and policy implications of AMOC collapse, I also have this example here from a paper that used basically an economic model to sort of calculate the social cost of carbon that would happen from different tipping elements. And I'm not, criticizing this paper here in any way. I'm just pointing out that because it only considered the AMOC temperature change, basically here you get that an AMOC collapse is actually good for the world, right? Because cooling versus global warming, you think that's actually a good thing. So the AMOC collapse reduces the social cost of carbon. But the issue is that if you look a little bit more into the details, you see a more complex picture. And so here I want today to have two examples showing you the sort of nuances of this global picture. The first is in the Amazon forest, and sort of look at the South American monsoon here in South America, specifically this box, where here on the left you have the sort of like, again, change in annual mean precipitation. You can see that it's, maximum half of a millimeter per day drying, which doesn't seem a lot in the Amazon forest, which gets like, 10 millimeter per day monthly precipitation. But if you look at the sort of like seasonal impact, and we'll look at that more in detail later in case you're getting confused about the figure, but you can see that there's a shift of the seasonal cycle to later in the year. So overall, it doesn't look too bad, but then if you look at the details, it could be quite catastrophic. And similarly, if you look at Europe and the temperatures, here on the left, you see that overall you have cooling of the surface temperature of all over all of Europe. But if you look in the summer, in some regions of Eastern Europe, you have an increase in heat wave despite this cooling. So these are my two examples. I don't have enough time to go into a lot of detail today, but to start with the sort of Amazon rainfall one, this is sort of based on work that I led with a lot of other great colleagues, basically using data from the North Atlantic Housing Model Intercomparison Project, NAHOSMIP, where you have these 4 different models where we have the AMOC housing in gray, and then the AMOC housing is stopped, and you have a weak AMOC state. And this is just really useful because we can now compare the black and the orange in multiple models and, sort of work around also these model biases that sometimes come into play. And you can see that if we look at the different models, the sort of change in precipitation is different in the models. Sort of basically it's correlated with how strong the change is. If you have a strong AMOC decrease, you have a strong precipitation change. A small AMOC decrease, you have a small precipitation change. But the pattern is the same everywhere, right? You have this sort of southward shift of the tropical belt. And the fact that the pattern is the same in all the models allowed us to make some more sort of robust statements about what happens when the AMOC collapses. So in this paper, we specifically looked at monsoon regions where sort of, again, different definitions for what a monsoon region is, but basically we think of it as somewhere where this sort of like tropical, the ITCZ, this intense band of tropical precipitation, impacts the seasonal changes. So in this presentation, I'm going to be talking about 2 of these sort of monsoon regions. One of them, which is the sort of like one with the sort of but sort of nuance, is the South American monsoon, the part of it that's north of the equator. And the one that's more straightforward that I want to show you in comparison to the other one, sort of in contrast, is the West African monsoon. And the reason that I'm putting these 2 systems in contrast is because basically in the West African monsoon, and I apologize for the graininess of this image, but the cluster was off last week, so I couldn't make a better one. But in the West African monsoon, you can see that the rain belt is sort of like coming in, causing a rainy season, and then coming out, right? And then, but in the sort of like this part of South America, the rain belt is sort of going in and out and then in and out and having more complex impact over the continent. So basically what happens when the AMOC collapses and this whole rain belt shifts to the south is that in the West African monsoon, here you have this little GIF image on the right, and you can imagine that before the AMOC collapses, it sort of comes in and out, and then when this whole thing shifts southwards, it comes in a little bit less and comes out, right? And you can see this here down here. You have the sort of x-axis is the season, the sort of different months. It's the seasonal cycle, and basically red is a decrease in rainfall of this sort of like rainfall seasonal cycle. So for example, if you look at CSM, before the rainfall went up to here, the AMOC collapses, it only goes up to here. So you get a sort of similar, wet season and dry season, but the wet season and dry season, like the wet season is much less wetter. So you have this decrease in the wet season everywhere. It's pretty sort of like clear what's happening. The rain belt is just not coming in as much into this region. But what happens in the sort of northern part of the South American monsoon, so here I'm showing, the seasonal cycle in this box here on the left and the sort of similar image here, is that before, the belt was sort of like moving in and out sort of over it. And then after the collapse, the whole thing shifts southwards, but it's not such a clear sort of, like basically reduction of one wet season, but actually the sort of time at which you have the peak of the wet season comes later. So it's clearest in HGM, where you have this sort of like 3-month shift into later of the year, in the year of the wet season. It's a little bit, different depending on, how strong the AMOC collapses in different models and exactly what's happening here. But it is clear that you have this decrease in rainfall and then an increase in rainfall, because the whole sort of like up and down movement of the rain belt shifts. And you can also sort of see this when you look at, you sort of calculate the dry season length in these regions. You can see that in the West African monsoon, it's very clear that the dry season is getting longer in some regions by 1.5 months, and some regions a little bit less. But here in South America, you have this sort of clear thing that below the equator, it's just getting more rainfall, but above it, the dry season is actually getting longer. Even though it's not just shifting into later of the year, the dry season is also getting a little bit longer. Okay, so this was my first example. The second one that I mentioned before is to do with European temperatures, and this is based on the work of my colleagues from Italy, Virna Mettia and others, and published in 2 papers from 2024 and 2025. They use a similar model where you hose the AMOC, and then you have sort of like this sort of weak AMOC here, and they use the sort of sea surface temperature and ice from the weak AMOC to run AMIP style simulations. So they have a lot of ensemble members and they can look at extremes. And what they see, first of all, in sort of annual mean, is that in the winter, and now the slides are going to be sort of like left part in the winter, right part in the summer, because impacts are different in the winter and summer. In the winter, you have this very strong cooling over this area of Europe and Greenland. And then in the summer, it's a little bit more localized, but still everywhere there's just cooling. But then if you look at the sort of like extremes and what happens to sort of like cold spells and heat waves, and basically a cold spell is just, extremely cold weather staying around for multiple days. Here, the definition is more than 6 days, basically. So you can see that in the winter, cold spells actually decrease over all of Europe. So even though all of Europe is getting colder, there's less of these sort of like long periods of intense cold. And similarly, in the summer, even though all of Europe is getting colder, you do actually have more heat waves over this sort of like Eastern European region. And the sort of reason that they see for this in the model is that basically the blocking frequency changes over Europe. So blocking is sort of like a weather concept where you have this sort of stationary areas in the atmospheric pressure. And basically you can think of it a little bit like a traffic jam in the weather, right? Where the same weather sort of stays around. And so in winter, you can see this blue region here is like this decrease in blocking over Northern Europe that corresponds to less cold spells. And similarly, in the summer, you have increase in blocking over this sort of Ural blocking region, which corresponds to this sort of like increase in heat waves. So because you have blocking, you have weather that stays around, that's sort of like a cold spell or a heat wave. Now, so this is pretty clear how these are connected, but then my colleagues were also, interested in why does the blocking change in this way. And so this is a bit more of a theory, because it is difficult to understand these weather phenomena in these models. But their theory is that it's connected to the Northern Hemisphere jet stream, which is this sort of like, this is basically the air currents, the winds in the atmosphere. So above the Northern Hemisphere here, and you can see that there's this sort of like narrow air current that affects weather in Europe. And sort of a very, very simple way to think about this is that if the jet stream is strong, it sort of moves weather systems pretty fast, right? It's sort of like a fast lane and when you're driving. But if the jet stream is weaker, it doesn't sort of, the weather systems are not moving as fast. And so you can get sort of blocking and you can get cold spells and heat waves. And what they do actually see in these models is that in the winter, the weaker AMOC is here in pink. So look at the difference between the blue and the pink. You can see that the pink here is stronger, sort of like the peak of it is at a stronger velocity, which means that the jet stream is actually getting stronger in winter and decreasing the blocking, meaning that there are less cold spells, even though it's cold. Similarly, in the summer, the jet stream is getting a little bit weaker and it's moving to the south, which, specifically in this Ural region, even though there's cooling, there's more blocking and more heat waves. So this is a very interesting theory, and it sort of explains what we see here. And obviously this needs to be sort of researched also in other models, but it is sort of like a way to show how counterintuitive the impacts of something like an AMOC collapse can be, and the fact that you need to look at the extremes as well. So this was all I sort of wanted to talk about today. And in conclusion, the big sort of impacts of the AMOC are very substantial just by themselves, right? There's a widespread cooling of the Northern Hemisphere, and this tropical precipitation band shifts to the south, basically taking rain away from a lot of regions that are used to getting rainy seasons. But it's also important to remember that the seasonal and extreme impacts can be more nuanced. For example, even though on an annual sort of level, the impacts in the Amazon forest don't seem that big, the seasonal cycle could be really bad because basically, you have people and plants waiting for the rain to arrive in one specific month, and then it arrives 3 months later. That can really sort of mess things up. And in Europe, even though you might just think, oh, it's cooling, that's good, you could actually have more heat waves, for example, and maybe less cold spells. I don't know if that's actually a bad thing socially, but definitely more heat waves is bad. So yeah, in conclusion, we just need a lot more detailed research to really understand the AMOC collapse. And if you want to know what it would do in a specific region, you really need to look at that region as well. But it is, I think, pretty clear overall, it is a bad thing over most of the globe. Yeah, thank you for listening. Yeah, I'm looking forward to the discussion, and I'll hand over to Laurie now.
Thank you very much, Maya, for this insightful talk. There's already first questions popping up in the Q&A box. Please, everyone, continue to put your questions there. I also encourage you to upvote questions you find interesting. And this being said, we will move on to our next speaker, Laurie Laban-Langton. Laurie Laban is an executive director of the Strategic Climate Risks Initiative, I think, and DoTank, that helps develop capabilities for securing a better world even as the environmental crisis escalates. He is an associate fellow at Chatham House, a visiting fellow at the Global Systems Institute at the University of Exeter, and an associate fellow at the Institute for Public Policy Research. Laurie is also an advisor to the UK Climate Change Committee and the Adelphi think tank, as well as a trustee of the New Economics Foundation. Laurie, I hand over to you.
Thanks very much, Annika, and Maya to you as well for that excellent presentation. And thanks all who are watching and listening for joining us here today. Let me just share my slides. Hopefully you guys can see that. Hopefully you can't see my presenter view, is that right? Perfect. Okay. So I'm going to talk about something that I call the security blind spot, a blind spot in how governments in particular, but also companies and other key institutions think about the risks from climate change, of which AMOC, as we've heard, is one, and one that should be taken more seriously. This presentation effectively explores the kind of things that might be getting in the way of key institutions being as concerned as they probably should be about risks like AMOC weakening and collapse. But let me start with a story from the UK, where I'm based. This is a picture of the House of Lords, part of the UK Parliament. Parliament has existed in this country for some 7 centuries, on and off. The official parliamentary record goes back to the early 1800s, I think to 1803. And in the 222 years since that parliamentary record began, there has been 7 mentions of AMOC ever. 3 of these were in a recent conversation, but a really interesting example of where it was mentioned was this question here, asked by a member of the House of Lords. This is Baroness Jones of Malzelcombe, and she asked the government specifically what assessment they had made of the effect of any slowing or collapse of the AMOC on economic planning. She asked specifically about economic planning. And this seems to be a pretty prudent question to ask based on what we heard from Maya just now. This is the response from the government minister. And the response was to say that they have not assessed the effect of any slowing or collapse of AMOC. And then there's a repetition there of some of the latest IPCC evidence. So how can this be the case? How can, on one hand, we be getting the kind of warnings that we've seen in Maya's presentation and from others, and yet we've got a situation where the UK government, and the UK government is not alone, is not doing an assessment of the effects of AMOC collapse on key things like the economy? We set out to answer this question in a report that we published last year called The Security Blind Spot. In that we spoke to a lot of people in the parts of governments that are focused on the major risks facing societies. Those bits are related to climate change, but often they are not specific to climate change. They are the bits of government that think about security. And by security, I don't mean defense or militaries, that is a part of it. I mean the bigger picture of human security. These are the bits of government that are anticipating things like the COVID-19 pandemic, and I'll come back to that later. And I'll work through this built on the warnings and work of others, including the actuarial profession in the UK, partly working with the University of Exeter, the Global Systems Institute, which also ran the Global 10 Points report. And then there are a number of fantastic reports and investigations that have come out in the last 10 or so years that have tried to grapple with this subject of how we think about climate risk and what the blind spots may be. I'm going to summarize some of the things that we learned across 3 areas: conceptual problems, analytical problems, and institutional problems. And I'll focus mainly on analytical because I think that's most relevant to our discussion today. But I'll start with conceptual because this is really important. It's sort of a key problem with the mental model of climate change that's often in the minds of those who are in very important bits of government. And that mental model is often fundamentally different from the mental model that climate scientists, that other people who are very close to climate analysis have in their minds. This mental model in the context of government is often that if climate change cannot be cleanly avoided, and there are still a number of people who do have that model in their minds, that we are going to definitively prevent a global climate crisis, though that view is starting to shift. And for those who realize that we're going to see grades of worsening impact, the mental model there is that they will primarily relate to first order impacts, to what we see on the news, to the heat wave, to the storms, and that they will evolve erratically, but steadily over time. The mental model here is like the image I've got on the screen, just more things like LA playing out over time. It is a mental model that excludes a lot of things, I'll get into that, but one of which is tipping points. And an example of that is represented in this report. This is a fantastic, in many ways, bit of analysis undertaken by an agency in the UK, a government advisor on the economy. Usually that advisor is looking at projections on fiscal policy. What will the deficit look like, the fiscal deficit look like over time, for example? It also now does reports looking at major risks to the economy, specifically to fiscal policy as time goes on. And it is extremely welcome that of late it has been doing reports that are looking at climate risk. This graph is from one of the recent reports, and it is looking at a number of scenarios, a baseline of no climate change, and then climate change that is limited below 2 degrees, and then limiting below 3 degrees. And what you're seeing there is time on the x-axis, and on the y-axis, you've got the drop in GDP. In the worst case scenario here, a 3 degrees, just below 3 degrees scenario of warming, you can see a loss of GDP to the UK of just under 5%. And that, of course, that analysis under their own admission does not account for tipping points. That is a specific example of that mental model represented in an analysis undertaken by an agency that informs government policy. And of course, what that means, as we'll get into, is that the idea that a 3 degree scenario is the kind of worst case scenario, that's how people in government will look at that, will lead to just under a 5% reduction in GDP is, of course, probably imprudent if you miss some of these big risks. So let's get into the analytical side. Let's think about the kind of things that would lead to that mental model being the way it is. The first is this wonderful acronym HIL, high impact, low likelihood, which I'm assuming many of you have come across. This is constantly used in connection to tipping points, AMOC or otherwise, that they are high impact. We've seen that from Maya's presentation there, and low likelihood. And we saw that in, you would have seen it in the answer, the government answer to Baroness Jones's question, where the minister said, you know, hey, the IPCC has been saying that this thing is unlikely. And in governments and other key institutions, unlikely or low likelihood is often construed as reassuring, as effectively, for some people, no likelihood. And there are a number of reasons for this. Firstly, the language is not clear to people who are not close to climate science. When the IPCC says very unlikely or unlikely, there are, of course, probability ranges that are associated specifically to those words. It can never be assumed that those probability distributions are in the minds of people in key institutions, even if you've explained it to them. Now, in the case of tipping points, some of them might have already reached the threshold that should trigger a response from government if those percentages, if those ideas of probability were explained to them clearer than just using words like unlikely or very unlikely. And a good way to understand this is that between the year 2005 and 2020, on the cusp of the pandemic, that 15-year period prior to the pandemic, the UK government, and forgive me, I will keep using the UK government because it's the one I know best, but what I tell you is relevant, I can tell you for a whole lot of other governments. Between 2005 and 2020, the UK government considered an influenza pandemic as the most significant risk of civil emergency facing the UK. And it judged the likelihood of that to be 3% in any given year. 3% in any given year. In any given year, there was a 3% chance of this occurring. That's what the government judged. That 3% was enough to warrant vast assessments, the construction and maintenance of early warning systems, strategies, huge governance arrangements, and even a cross-government exercise that was undertaken to simulate. And there were many other things. None of those things are being done for tipping points. But the question is, if the likelihood information was communicated better, might that be clearer to those in government? But even then, we can probably say that they're not and have never really been low likelihood, or indeed that we've been able to say low or high likelihood in relation to tipping points, however much that might be changing now. They're actually, from my perspective, high impact, high uncertainty events. Though, of course, the acronym is less, high HU is much better than, is not as good as HIL. And governments have been warned consistently that in the face of high impact but high uncertainty events, they have been thinking about them wrong. They have been fixating too much on likelihood. If there's high uncertainty around the likelihood, that is a big problem It doesn't mean that you should fall back on assuming low or no likelihood. It means that you just have to grapple directly with that problem. And this here is from the recommendation of a major report that investigated the UK government's national security risk assessment process that made the point that likelihood should not be the main driver for prioritization of risks when it is very difficult to assess them with high confidence. And instead, as you can see there, there should be a paradigm shift towards decision making that looks instead at impact versus preparedness, instead of impact versus likelihood, which is the current way of thinking about it. And governments have a track record of doing this with other risks. This image here is of a simulation exercise undertaken in London to simulate there being what is often described as a marauding terror attack. This is an attack on a shopping mall, or like the terrible events we saw in Paris a number of years ago around the Bataclan. Those are high impact but high uncertainty events. But they are still, governments are still able to grapple with them and think about them and assess them and exercise around them. Which points to another key thing for us to bear in mind, which is that the government is clearly connected to different thresholds of information that would trigger their focus, like we have seen a focus on counterterrorism over the last couple of decades. And that threshold of information isn't necessarily a better quantitative model that has improved the resolution and reduced the uncertainty bounds on, say, a likelihood calculation. Because the critical bit of information that led to a focus on counterterrorism was not because the counterterrorism analytical world had developed far better counterterrorism models equivalent to our Earth system models for terrorism. There were other bits of information that were critical, and thinking about what those bits of information were and what the politics that sat behind them are really important in helping us confront how we might think about the information that's critical for decision makers now. It is not because they built better models. And another frustration there, or part of that, is that there's an intuition missing in relation to climate change that exists in relation to things like counterterrorism, like state conflict, like trade disputes, like geopolitical instability within governments. There is this concept of a risk currency. It's a technical phrase, but this is the way of decision makers think about risks and whether or not those risks are intuitive. If you go to a decision maker and you talk to them about a terror threat or geopolitical competition with China or Russia, they already have an intuition about those risks. They are also risks that touch on their pain points, the things that they worry about day to day, politically or from a policy perspective. With climate change, we don't necessarily have, and with tipping points specifically, that type of intuition. And that's for a number of reasons. One of which is that terrorism, state conflict, geopolitics have existed for a very long time in the mind of governments and states that have been around for hundreds of years, and there is an institutional memory that's carried on. Climate change is relatively new for those governments to be thinking through. So that intuition doesn't necessarily exist. Terrorism, state conflict, those kind of things are very intuitive to key decision makers. Tipping points, not necessarily. And that is not helped by a key cultural clash. We can help understand this by thinking of the phrase conservative risk assessment. That means different things to different people. To people in government, it means including as much stuff as possible, like this example here of the design basis for nuclear power plants in countries around the world, including the UK. They are built on a design basis to handle 1 in 10,000 year events. These nuclear power plants probably will last a few decades. So this is many orders of magnitude above the lifetime of those nuclear power plants. That is a conservative risk assessment. It is erring on the side of including risks and not excluding them. It doesn't mean conservative in the sense of, oh, we're not sure about that, so we won't include it. It's, can we rule that out? No, we must definitely include it then. And decision makers err on the side of inclusion and not on the side of exclusion. But when they're talking to other people, including climate scientists, they're assuming that climate scientists also err on the side of inclusion and not on the side of exclusion. And that can be, that can lead to some misunderstandings about the information they're receiving. And finally, my last point about the analytical blind spots relates to what actually is decision useful. So I've nabbed this from my presentation. Images like this are absolutely critical. They are so important for us understanding the potential impacts on AMOC, as well as a number of the other things it might have showed. But it is not enough for a decision maker. I'm not suggesting that that's what I was saying. These are the things that are decision useful, are needed by decision makers. Impacts on trade, impacts on inflation, impacts on great power competition and conflict, impacts on geopolitics. And we are still not yet, from my understanding, at the point where we have the information about the consequences of AMOC collapse and so on that would be really decision useful. Analyses like this, from a paper developed by colleagues of mine at the University of Exeter, that looked at the impact of AMOC collapse on the farming of the UK, on arable crop growing, are getting there, as is this analysis undertaken by colleagues at GSI for the OECD that looked at the changes in crop suitability. But we still need to go further to look at then the cascading consequences. What would those things mean for trade, for geopolitics, for great power competition? And of course, that requires quite a significant cross-disciplinary effort to get that for tipping points. And we need it more generally, because I think one of the major features of our experience of living in climate change, and what decision makers will then have to worry about, will be these cascading consequences, whether they're triggered by tipping points or not. And this is a graphic developed by colleagues of mine at Chatham House that did an analysis of various cascades. Here for the food system, cascades that we're seeing playing out in Europe, where we know that extreme weather events have been driving inflation, and inflation has the consequence of then impacting the cost of living, which has been one of the central political features of recent times. But we're not helped by the fact that governments in general struggle with these cascades. And again, they have been warned about this recently when it came to the pandemic, and a failure to have mapped the interdependencies between a crisis that went from being a health problem to an economic, a social problem, a political problem, a problem of trust, and so on and so forth. So in developing that cross-disciplinary effort to really provide those decision useful analyses of tipping points, there will have to be a process of grappling with the existing blind spot in thinking about cascading risks in general and governments. Finally, institutional problems. So governments are simply often not really set up for risks like, say, AMOC collapse. They have departments like this. This is our primary environment department in the UK government, that are often, they're not at the heart of strategic decision-making at government. They also undertake risk assessments on climate change, which are then by definition disconnected from the heart of government, marginalized often. And then they often undertake risk assessments that, or as a result of that, they don't undertake risk assessments that look at the overall security consequences of these risks. For example, the UK government does do a regular climate change risk assessment. It is excellent. It doesn't have within its purview a focus on the overall security situation resulting from climate change, including, for example, what is the worst that climate change could throw at us? For the UK, that might be AMOC collapse. What are then the cascading consequences of that, and so on? And then all of that is not helped by the fact that government is very messy when it comes to some of these big issues. Here is a picture of the national security policy landscape in the context of the UK. There's similar images you could draw for governments around the world. And then when a crisis hits that, this is what ends up happening. This is a messy diagram developed to try and understand how the government thought of responding to COVID when it came along. These are one of the spaghetti diagrams that our official inquiry here in the UK developed to try and understand what was going on. And then, of course, sitting above all of this, we're not helped by the fact that governments have not done enough to ensure that we're resilient to baseline climate change, let alone tipping points. So, what do we do about this situation? What do we do with those blind spots? And I will quickly rattle through some final thoughts on that. And then I'm very interested to see what people's ideas are based on that. So the first thing to say is that, well, the existence of tipping points clearly requires a much more strident action on climate change from governments. We need to reduce emissions far quicker. We need to invest in adaptation, and we need the kind of changes to our systems that can make that happen. And I totally agree with that. But we're in a bit more of a complex situation, because that story of, hey, there are these tipping points and we need to do everything we can to avoid them, is one that I strongly agree with. But it's still a story that's very similar to this situation, that the world is like a ship heading towards the storm being going over 1.5, or climate change in general. And we need to do everything we can to persuade people of the existence of the storm, and then to motivate them to work together to change the bearing of the ship, to change the development of societies, so we ultimately avoid the big storm of climate change. But the reality is more complicated than that. In many ways, we are entering that storm. In many ways, the potentially escalating risk of AMOC collapse is a sign that we are now within that storm. And this is where a case study of mine jumps to my mind of then what we will need going forward, the capabilities that we will need going forward to handle this situation. And this is a scenario not in which AMOC collapses, but in which the deep convection in the North Atlantic subpolar gyre was, say, to break down. In this scenario, my understanding, and I'm not an Earth system scientist here, but is that we would face basically a bit of a critical action moment. We would have to be working even harder than ever to deal with the potential for further weakening, collapse of AMOC, but we could be distracted at exactly that moment by handling the adverse consequences of the collapse of deconvection in the North Atlantic subpolar gyre. And that's a very difficult situation for governments to get their head around. That is a situation that is similar to us being within the storm of climate change, right? The navigational challenge has shifted. It's no longer about cleanly changing bearing and sailing around. It's now having to navigate bits of the storm that are very disruptive and to navigate them effectively so that you ultimately avoid bits of the storm that we must avoid, like AMOC collapse. And one of the big fears, one of the big concerns that we have is that if we carry on as we are without these capabilities within government to properly get their heads around tipping points, if we had this scenario where there was a collapse of the North Atlantic subpolar gyre, that it would lead us to handle that situation very poorly. And the critical element of that is that it would derail us from being able to focus on the type of decarbonisation and other action that would be needed to stave off a worse situation, which is full AMOC collapse down the line. And that is something that we call derailment risk. The idea that the worsening consequences of climate change that are hitting us could create situations in which we are unable to properly deal with the causes of climate change. And we went and spoke to a bunch of sailors about this analogy we're using to try and understand from them what the key capabilities are that are needed to ensure that we can become better navigators now that we're in the storm of climate change, because those navigational capabilities are different than the ones you need to definitively avoid the storm of climate change. And I will very quickly rattle through the 5 areas that we learned about. One is that we need better situational awareness. Our radar for spotting the bits of the storm that are unmanageable and we must avoid, and our radar for spotting the bits of the storm that might be unavoidable and we'll have to better manage. That radar right now is not very good. One of the ways for us to improve that is by doing far more scenario exercises that include the kind of cascading risks that are decision useful. So that means switching from an attitude of risk assessment as quantifying things like economic impact, the unusefulness of which Maya presented just now, into storylines that look a bit more like this, where this happens leading to this effect and that cascade and that cascade and that cascade. When we then connect that to early warning capabilities, and in the UK here, we've had investment from an advanced research organisation sponsored by the UK government in early warning, we can then start to do things that we call resilience games. We don't call them war games, we call them resilience games. Scenarios of things that could happen in the future. SPG collapse or not, SPG collapse leading to big AMOC risk or not. What do we do about the situations? Then, when we've got our radar better, we need speed. That's how you get out of storms at the end of the day. And by playing lots of scenarios, we can identify no regrets strategies for how we speed up, even under the duress of the storm. By that, I mean, if we have further AMOC weakening, severe AMOC weakening or not, we know that we will need buildings that better regulate extremes of temperature, for example. And we need those anyway. That's a no regret strategy. Again, with severe AMOC weakening or not, we know we're going to have to bolster nature because it will handle these, it will be facing these different shock scenarios. And we know that will be good from a number of other angles like carbon sequestration and improvements in food security. So in playing various scenarios through of the future, we've got to identify these no regret strategies. And that is critical because when we talk to decision makers about tipping points, which they don't really understand, which are very scary when they do understand, or we talk to them about a polycrisis, which is so complicated, it is, but it's very hard for them to get their heads around. They need something to hang on to. And no regret strategies that work across many scenarios are at the heart of that. But we haven't mapped them. And that is a critical gap. But 3 out of 5 is that then we will, of course, have to become more resilient. We know there's an adaptation gap to be closed. But we also know that as we head deeper into this storm, and as we get scenarios like potential SPG collapse, continued AMOC weakening, we will not just have to become resilient to protect populations, we'll have to become more resilient to make sure that societies can remain focused on that navigational effort, on dealing with that derailment risk that I'm talking about. And this is where this image comes in. This is an amazing image that came out of the LA wildfires, which shows a house on a street. The street was completely destroyed by the LA wildfires, but this one house survived. And it survived because it was built under passive house standards. So this is a house that prior to the wildfires was lower carbon, lower bills, and better for people's health. And it also was better adapted. This is an example of what I would call strategic resilience, of things that are no regrets, additionally, because they will make us more resilient. These are the kind of things that we need. These are the kind of approaches, design approaches to resilience that we will need to navigate this ship through the storm. But again, we have not necessarily mapped what the no regret strategies are that also include this resilience as well. The 4th out of 5 is leadership. You need a very different style of leadership within the context of a storm than the one you need to navigate around a storm. We don't have that right now. We have an approach to crises, to major shocks, that's about trying to return back to normal as quickly as possible. Normal is breaking down. Normal now is an abnormality of worsening climate change, and we have to avoid shades of more catastrophic abnormality like AMOC collapse. And we don't have the governance structures for making that happen. We do have governance structures for other major crises like pandemic threats, however much they've not worked so well in the past. But we now need them, sorely need them for things like tipping points. And I would strongly recommend you guys check out the governance sections of the Global Tipping Points report that I had the pleasure of contributing to, that was released in 2023, and we have again coming out this year. And then finally, fifthly and finally, we need stories to make sense of all this. Our climate stories are breaking down in their usefulness. The binary stories of win, lose, sail around the storm are clearly not making sense anymore. And we do need stories to make sense of things like the risk of tipping points, things like the risk of AMOC. And we haven't necessarily got those yet. We have had stories that have existed in other major crises moments, storytelling from governments to make sense of those crises and to keep populations focused on navigating them. We're going to have to work those stories out now because some of these things might happen and we have to avoid even worse things like AMOC collapse. And we will need the stories that make sense of this new, much harder part of the climate challenge that we now face. And I will finish there. That wasn't just about AMOC, because I think that AMOC is an interesting case study of how we think about the blind spots in our approach to climate risk more generally and how we navigate this next stage of what happens next. So Annika, I'll hand back to you and thank you very much for listening, everyone.
Thank you very much, Laurie. That was also super interesting and I think a nice combination between the two talks. So let's move on to the discussion. There's already plenty of questions coming in and I see that a few have already been answered. That's fantastic. I thought maybe we start with a few smaller technical things because there seems to be some questions in terms of understanding. And I would start with you, Maya. I'm trying to tie some questions together. So there's a question around, once more, the definition you made between collapse and tipping with the AMOC. Maybe you can just reiterate what you meant with this and how this is relevant or not so relevant for the policy questions that that came up later. And then also some questions around timelines, like when will the AMOC shift or collapse or things like this, and have we already seen impacts of climate change in general? I hope that makes sense.
Yeah, I guess, I mean, to start from back to front, have we seen impacts of climate change? Yes, of course, we have seen a lot. I would recommend you go look at the climate attribution, weather attribution works, right? Where they sort of like do these calculations about extreme events, you know, how more likely they've been made by climate change. They have definitely been made more likely. I mean, we're getting close to 1.5 degrees of warming now. We are seeing the effects of climate change all over the globe. Yes, and then we go back to sort of what I was saying about tipping versus collapse. So, I mean, the idea of tipping in general is that there are these systems which have sort of like this characteristics in terms of, you know, their dynamics, how they sort of like work, you know, when you model them or something. And you can think of, you know, a simple example is something like a chair, where it's sort of, you know, it's sort of stable where it's standing, and then you can like go back and front a little bit, you can tip back, and then at some point you reach this sort of tipping point at which the chair collapses to the ground. And sort of the reason that tipping points are something that we worry about in terms of future climate change is, first of all, because this sort of tipping, this fall down is abrupt. There's a lot of, you know, feedbacks that are strengthening this sort of like change from one system to another. So in the AMOC, this is a collapse, but, you know, for other systems, it's a transition to a different state. It's not always a collapse of something. And so in the case of the AMOC, basically, yes, so we worry about the speed. And also then the thing with the chair is that, you know, if you put the amount of energy you need to put in to sort of like pick up a chair lying down to make it stand up again is a lot more energy than you need, you know, just tipping a chair backwards is a little bit. So, you know, we might cross from, you know, some degree to like a little bit of, you know, 0.1 degree of warming will make the AMOC collapse. But then if we want the AMOC to be restored, we would have to maybe even cool back to temperatures of 1850 or before that. Or maybe, you know, just practically we would never be able to get the AMOC back to as strong as it is today. And similarly with other tipping elements. The issue in actually, you know, finding out whether something is tipping or not is that the rate at which we're warming the climate is extremely fast. It's, you know, unprecedented at any sort of like thing the Earth has seen before. So this sort of concept of abrupt tipping, in a way, isn't that useful when already the speed of warming of future, you know, emission scenarios is extremely fast. So that's why when I show you an image of, you know, what climate models project for the future, yes, it looks like the AMOC goes from, you know, strong to zero in about 150, 200 years. But, you know, we don't know if that's just because the warming is really, really fast, or because the AMOC actually is, you know, collapsing on itself because you cross the threshold. So to see those sort of thresholds, we do separate experiments. So yeah, that's the sort of like difference between tipping and collapse. In terms of the impacts, basically it's more about the irreversibility, right? The impacts come from the difference between the strong AMOC and the weak AMOC. Obviously, there's also differences in what, you know, triggers the AMOC to collapse. If you're having a sort of collapse that's not a tipping, you probably need a lot more forcing to get into that way, you know, like you need a lot more warming. So maybe the way that it impacts combined would be more complicated. But in terms of, you know, just the AMOC impacts by themselves, there isn't really a difference between collapse and tipping, just in terms of, you know, how reversible it is. Right, sort of like, so something like a simple linear collapse that isn't a tipping, isn't a transition to an alternative state. You could imagine that a little bit of, you know, basically cooling in some sort of, carbon removal, negative emissions, I don't know, could get us back to a stronger AMOC, where if it's tipping, then that's permanent, and it's sort of, we would likely not be able to reverse that. So yeah, I hope that answered the questions.
Thank you. I would pass on to Laurie. There's a question around the terminology of the high impact, low likelihood events. How would you change this language and terminology to better motivate action and facilitate understanding of policy for policy and public audiences? And I think you made a suggestion around this. The question here is also aiming at the term tipping points as well, and asking whether for a planning perspective, this might not be a useful term to capture the complexity of the systems and how the impacts will be felt. What do you think?
The key lesson from all of the assessments of government risk assessments has been, in general, to move away from any kind of obsession with likelihood. That's very difficult to do in practice, but there is an opportunity for the climate analytical community to work with other communities in, say, public health and pandemic risk, in other more security-focused, defense and security-focused subjects, to try and push that paradigm shift in thinking in government. There's a real opportunity to do that, right? And I think that tipping points are a good example of how to support that allied cause of getting governments to move away from effectively a risk assessment matrix that is impact versus likelihood to one that is impact versus preparedness. And that is common in so many other domains, right? Stefan has rightly pointed out here in his point about a 1 in 10,000 year event when you have multiple nuclear power plants globally is doesn't give you so many good odds. But the point I was making there more is that at least when they are planning nuclear power plants, their conception of conservative is to err on the side of including risks and focusing, of course, on the worst case. And one of the excellent points that's been made by my colleagues at the Institute and Faculty of Actuaries in the UK and the University of Exeter is that again is common, say, in the financial sector, where when you're an actuary and you're working with, say, an insurer or a bank, you are looking at the extreme end of the distribution all the time. You are making sure you're developing capabilities for how you operate that financial institution that are based on basically the worst that could happen. And a similar shift here is to basically say, okay, well, high impact, low likelihood is really an unhelpful thing for actually doing risk planning. We have to understand that events are high impact and maybe high uncertainty. However much there's actually information suggesting that, we're getting more certainty about likelihood. And then move away entirely from that kind of framing to focus more on asking the question, well, what is the worst that climate change could do? I would definitely put things like AMOC collapse in the answer to that question, and then working out the no regret strategies for that now painfully large scenario space of what could happen in the future, AMOC or not, SPG or not, list goes on and on and on. And those kind of no regret strategies are absolutely critical. And this is connected to the answer of one of the questions here about my point about SPG and AMOC as a scenario. We have to, I think, move towards an idea of what we describe as climate adaptation as not just us having to make up for lost time on that and to close the adaptation gap globally that the UN and others have been warning about, but understand that certain types of adaptation can be enablers of mitigation under conditions of duress. Right now, if there was SPG collapse, I don't really know what it would do, but I understand that it would be disruptive for a country like the UK. I know absolutely that it would be extremely poorly adapted to that. And I know that that would have massive social, political, economic consequences, which, if the UK was called upon to play a part in a collective effort to stave off further AMOC weakening, less worse things happen down the line, that social disruption will get in the way. So better adapted UK has got to be, as the UK hopefully gets better adapted, as other countries get better adapted, they've got to understand how the adaptation is not just about protection. It's not just about defense. It's actually about offense as well. It's about ensuring that our capability to act is maintained even as worsening things happen to us.
Yeah, there's a lot to prepare for. We have two concrete questions about impacts, whether those might be due to AMOC or changes in the AMOC in the chat. So Maya, I think these are for you. One question is regarding drying trend in the Congo Basin. And then the other question is in regards to heat domes, if either of these things could be affected by AMOC change.
Do you mean right now in the historical record or in the future?
I mean, they both sound like they're about, I mean, the heat dome is not specific, so I think that could be either. The other one is an already observed drying trend, but I think both directions are
okay.
probably interesting.
Yeah, so in terms of historical AMOC change, that's a little bit of a tricky one because we're not sure exactly how much or whether or not the AMOC has already been weakening. And there's also obviously been a lot of sort of, my feeling would be that the warming trend, sort of the impact of climate change in general and warming would be a larger signal so far than just the impacts of an AMOC weakening. So obviously a lot of things are changing. And yes, they might just be because of warming. I don't really know much about heat domes, so I'm afraid I don't even know. I haven't seen any research about AMOC impacts connecting to that. It's sort of AMOC impact is a very starting field, as I showed. But in terms of the Congo, I actually think that in that region, there might be more precipitation due to when the AMOC collapse in the tropical precipitation belt shifts southwards. Again, this I would have to check, but if you have a look at our paper or some other papers where you have these global precipitation maps, you can, zoom in onto the region of interest and have a look. I think the Congo region might actually have longer wet seasons due to an AMOC collapse. So likely the current effect isn't due to AMOC changes.
This makes me think that maybe it's also good to point out once more that we are currently potentially seeing competing effects, right, between global warming and then AMOC weakening if it is already happening. And you mentioned earlier that these hosing experiments that are used a lot, that you've also worked with to study AMOC collapse, that one shortcoming in these experiments is that you don't really study the effect of AMOC collapse and warming simultaneously. So if you could run any experiments on Earth system models that you would like to understand better what might happen in the future in regards to AMOC collapse and impacts, what would your ideal experiment design be?
I mean, the ideal experiment design, obviously there are experiments where people use an emission scenario plus like some hosing to sort of induce an AMOC collapse. But I mean, the experiments that I showed at the start of the presentation where the AMOC collapses sort of naturally just from warming, those are already very interesting. And yeah, I think there are people already looking into those, but it's sort of very recent results. Also, we are also, looking a bit more into sort of like how AMOC impacts change with negative emissions. So, if you have overshoots and then you go back, or if you stabilize the climate at different scales. So with all these sort of like nonlinear systems that react differently, it's always interesting to see. But yeah, I think the experiments that I'm interested in are already ongoing.
That's good to hear. I'm looking forward to the results that are in the pipeline then. I have a question here to Laurie. It's kind of a meta question about risk that has to do with risk perception. So because you're arguing that there needs to be, basically awareness needs to be raised with policymakers and also the public in regards to potential tipping events. I think I should probably read the question. I worry about the potential impacts that future pessimistic signals from early warning signals may have, for instance, rapidly shifting society's risk perception from these unrealistic GDP loss scenarios to more realistic and much more severe GDP loss expectations. For Iceland, I worry that a rapid perception shift might trigger a full-on societal collapse through effectively a bank run on the Icelandic economy. What do you see as the potential risks that the UK faces from such a rapid risk perception shift?
So this idea exists in, say, the domain of economics. It is the concern of a climate Minsky moment, named after Hyman Minsky, who studied financial crashes. An example of a Minsky moment is the financial crisis, where reality began to diverge from expectation for people in financial markets. And then the people in financial markets panicked, and it created a runaway process of that panic, creating a wider financial crisis. The concern here is that if we are in a situation where the risk assessments that financial actors, but society more generally, are using about climate change are unrealistic, and they are. We got a situation like I showed with my presentation. We have pension funds who think that a 4-degree scenario will only reduce their pension funds by 1%, for example. So these things are unrealistic. Their model of the future is kind of like this, and the model of the future is probably going to be something like all over the place. And when it's clear that that divergence is occurring, what Paul is asking here with the question is that will then cause some kind of reaction in society. And per the question, it might be that things like tipping point early warning could play a role in leading to that type of dislocation of expectation shock, right? And this is a particular question for those who are working on early warning of tipping points, because if we did get high resolution warning, we don't know if we will, but let's say hypothetically we did, then could it be something that shocks people? And there's clearly this dislocation of expectation. For example, if we had early warning that SPG collapse was going to occur, and that led to an unexpected sea level rise that's outside of the scenarios of the insurance market on the east coast of the US, that could cause a pretty big shock, which could cause a financial crisis. And my answer to that is that there is no clean way of resolving that situation. I think that there will be grades of shock when there is the greater manifestation of climate risk in current years, that effectively there's a vast amount of undisclosed climate risk that is growing and growing and growing. It will be disclosed, probably because it will happen to us as it already is, more than it is then disclosed through more reports or even early warning systems. But this is why it is critical to have a managed approach to far more realistic risk assessment. It's very clearly needed in the case of financial markets, so that when, for example, insurers have to move together or pension funds have to move together to expose this underlying risk, they can do so in a way that wouldn't punish first movers. Because if you're a pension fund right now and you put your hand up and you said, actually, we're going to include AMOC collapse in our scenarios and we've done the analysis and it would be devastating for us, they would probably be punished by financial markets. So there has to be this managed disclosure process, or else there will be these second order effects, basically, these knock-on effects. And that will come, it is critical that that's done before time, because that being done, being forced on us by the Earth system, will be way more disruptive. And this is why you have to look at the efforts of climate campaigners who say, I mean, when Extinction Rebellion occupied London in 2019, their first ask was tell the truth. And from a technical perspective, that's a very smart ask, because the longer we leave that, the more disruptive the disclosure of that risk will be down the line. So there's no way to fundamentally resolve that, but it is very important for governments to upgrade their risk assessment capabilities and for regulators to make others upgrade their risk assessment capabilities, because the revelation of that undisclosed risk later will be way more disruptive than admitting it now, but they will need help to do that together.
Nice, thanks. I think, Maya, you have a question for Laurie. Is now a good time?
Yeah, of course. Thanks. Yeah, I mean, I really enjoyed your presentation, Lori. It's really good as a climate researcher, also after years of just, sort of doing the science, also to hear someone talking about the actual implications. But I was sort of wondering about the issue with timescales, because, the examples that you gave, something like a pandemic, something like a terrorist attack, it sort of happens, the thing happens and immediately it's catastrophic and you need to sort of like address it. But with something like an AMOC collapse, like a tipping point, it's not, it doesn't happen at the same time scale, right? An AMOC collapse, you sort of pass the threshold. You're not even sure if you pass the threshold, probably for another 5 years. And then it takes another 50 years to reach the actual bottom. Obviously, it starts to get bad on the way. Something like an Amazon, deforestation might happen a bit faster, but something like the ice sheets obviously happens over like centuries. So how would you sort of like have these, I think you didn't want to call them war games, but I forget, I think it was adaptation games or something, I don't know. But yeah, how would you sort of set up those scenarios for a sort of catastrophe that happens over such a long time?
It's a great question, and it's one of the main things that we have learned from our approach to what we call resilience games so far. So we did develop a very rough prototype version of this on SPG collapse, and one of the key things we learned from doing that with various people is that we have to better understand the timescales that you're talking about. So there's the sort of biophysical timescale, which is the longest. Say in the example that you're giving, it's shorter with, say, SPG collapse, from my understanding. Then within that, you have a timescale of basically things like, well, the adaptation of your infrastructure, of your food system, agricultural production, and so on, that exist on different timescales within that. So let's take AMOC weakening or maybe SPG collapse, which leads to colder conditions that are maybe unexpected compared to how people are thinking about adapting infrastructure to climate change. There will then be a lag time in which the railway lines, the power cables, the houses, the public health system, the farmers, etc., will have to undertake resilience measures to deal with the emergence of the new reality and then living in that new reality. So you've got the biophysical reality. You've then within that got a time period of the sort of what is required to deliver adaptation. And then even shorter are then these political time periods. And those are the ones that we surfaced as being of most concern. So let's just take SPG collapse only because it's shorter. If that's playing out over a period of, say, I don't know, 10 years, that's 2 parliaments. That's almost a generational span of time politically. And 10 years for the information cycle is like an epoch. Think of what we were talking about in 2015. And so what we surfaced in doing this prototype resilience gaming so far is that we just don't have the capability. We might have the capabilities to deal with the adaptation time horizon, but that's still big questions about how you would undertake emergency adaptation, say, for agricultural systems. But we are totally missing the capabilities for the political information cycle, for example. And so what we're proposing and what we're hoping to do very soon is to undertake a major resilience gaming exercise for AMOC collapse, in which we would try to surface similar issues that we're playing around with there, to then identify the capabilities that we could start to develop and the possibilities for how to take that agenda forward, basically.
Thanks. Yeah, that sounds like a good idea.
We have a few questions that are geared towards the tipping point, cascading tipping points and impacts for policymakers, and whether planning around this is already happening. I think in a way you've answered most of it, that not enough of it is happening and not very much of it is happening. And also the question around funding. Is there a funding gap in regards to this kind of research? Maybe you can give a very quick summary once more.
I mean, I'm interested to hear Maya's answer on funding. I think that it is eye-wateringly underfunded, these risks. This is common in human societies, that major risks are under researched, and that research is under invested in, and that really has to change. It is from my perspective, it is simply unacceptable that at this late stage, as we head over 1.5 degrees, we are still in the situation where key strategic decision makers in governments and financial markets and the humanitarian sector and so on are not being given decision useful risk assessments of risks like AMOC weakening and collapse. It is unacceptable that that is the stage now, and there needs to be far more research. Now, to be very clear here, we know that those things are bad, but as I went through, we haven't got the information that helps other decision makers appreciate how bad those things are. When we did our work, we went and spoke to people who should know what these tipping points are, and they didn't even know what they were, partly because they didn't have this decision useful information. But we also need it, as I was saying, not just to warn of stuff we must avoid, but to better identify things that we might not avoid, which will be critical to us being able to navigate what comes next. So from my perspective, it is a chronically underinvested area, and that is unacceptable. And I will quickly tack on an answer to the question about whether there is lots of planning going on in these areas. There isn't, as far as we have seen, and that's partly because these are huge issues. They're relatively new. They're very complicated, as I've been talking about. And this is why we are proposing things like scenario exercises, because they are existing methods, well used and well understood by decision makers and planning authorities, that will then help them move this conversation onto a tangible discussion of what capabilities we need and what we do next. And again, it is late in the day for that, but that is a critical next step that's needed.
Right, thank you. I have in the Q&A box a sort of dissenting position that I think both of you can maybe answer. So on the technical level, I'm guessing it's more a question to you, Maya, but I think on the policy implication, it's also a question to you, Laurie. There's actually two questions or comments rather by Ray Schmidt. I will read out the second one because I think it contains sort of the point made in the first one. So Ray says the AMOC cannot collapse, and there is no evidence that there has been any decrease in the AMOC in the observational record. He continues to say that the housing experiments are fantasy and that the Greenland ice sheet cannot melt fast enough to counteract the ongoing salinification of the North Atlantic. I will shorten it a little bit, but his conclusion is that using housing experiments that are, well, not entirely, they're experiments designed to explore the impacts of AMOC tipping, right, and not the likelihood of AMOC tipping, that they shouldn't motivate climate action. And Stefan has responses to these that I think everyone can go and also have a look at. But what do you guys say? Because I'm sure it's also not the first time you hear questions of this kind.
Yes. So this is also something that you run into when you talk about, uncertain events. Also, there's sort of like always some uncertainty, but I do think that there's a long list of evidence for why the AMOC might collapse. We're not certain yet, but it's certainly not, a fiction, right? First of all, you have paleoclimate evidence. So we have sort of like records of past climates where we see these abrupt transitions in the climate. So we already know the climate definitely can undergo abrupt changes. And a lot of these sort of changes, for example, have a look at, Danska Østgård events, sort of have been theorized and have been sort of associated with abrupt changes in the AMOC. So we have a good reason to believe that the AMOC can change abruptly. And then, we have this like long list of different models. We have extremely simple models where you basically model the AMOC as just a few boxes. And you have these extremely complex models where, you're, like I said, you're parameterizing every little box of, with all the physics and all the understanding that we have, and you run it over years on supercomputers. So we have this huge range of evidence. And obviously, not all of these models have shown an AMOC collapse, but a lot of them have, right? The simple models very clearly show this sort of dynamical structure where you do have these two alternative stable states and you do have bistability and a collapse. And then when you get to these complex models, some of them show a collapse due to warming, some of them don't. The thing with hosing that we're showing, yes, I agree that the amount of fresh water that you are inputting to collapse the AMOC in these simulations is more than you would get, with just future ice melting, Greenland ice sheet melting. But what we're investigating here is not, is this the amount of fresh water needed? Because one of the reasons that the AMOC collapses in warming scenarios is the heating, right? Is also the sort of heating of the North Atlantic. So actually, in climate change scenarios, you have heating, and then also you have all these other feedbacks that happen, right? Including sort of the extent of the ice in the North Atlantic. But the important thing about these hosing simulations is that you can also hose the AMOC, right? Transition it to a weak state in a way that maybe is unreasonable for warming, in terms of the amount of fresh water, but then you stop the hosing and you see that the AMOC stays in the stable weak state. And so you show that the AMOC has alternative stable states, right? Which shows the possibility for the AMOC transitioning. Again, all of these are models, none of them are perfect, but you have this really wide range of evidence that shows that the AMOC can collapse. And then you have the experiments that I showed at the start of the presentation, right? That had no hosing. There's no sort of whatever, these unrealistic something, whatever. These are just emission scenarios, a different range. Some of them you might say are maybe extreme, something like SSP 585, but there's also even AMOC, you see the AMOC going from strong to almost zero in SSP 245, which is sort of a middle of the road future emission scenarios, right? So obviously we can't be sure yet, because there are still some models that don't show an AMOC collapse, but it's definitely not a sort of so the statement that the AMOC cannot collapse, I think, is not true, right? We know that it can collapse. So yeah, I don't know, Laurie, if you have.
Right.
Well, I don't know the answer to the question because I'm not a system scientist, but what I do know is that if a decision maker was privy to that question, this conversation, they would walk away being like, this is very confusing, which probably means I don't need to worry about it. I'm out. In the same way that if they were privy to the very technical discussions about the possibilities for a novel coronavirus or not, or the technical discussions about the possibilities of Russia invading Ukraine or not, or the technical discussions about whether the Japanese imperial government was going to attack Pearl Harbor in America or not, they would come away from that being like, that's all very technical. Everyone seems like they're disagreeing. It sounds like there's no risk, when actually there was, because you couldn't rule out those events. And in what is missing often from the climate world is a group of people called knowledge brokers. They are people who are as literate in earth system science as they are literate in how decision makers think and make decisions. Often we're missing them with climate. They are the people who can keep on top of the earth system science and sort of mediate from the discussion and say, okay, but at the end of the day, can we rule out AMOC collapse? If we can't, then I'm going to go over here and talk to the decision makers in the language that they understand. You would never be exposed, a decision maker, to pure, raw analysis about signals intelligence on a counterterrorism threat. You would be exposed to the knowledge broker who would help you understand and translate that risk. And we're missing that, particularly when it comes to tipping points, but I think climate in general. So this issue here perfectly illustrates the need for that knowledge brokerage between the complex analysis and how decision makers think and act.
Right, I think these are already very good final words, because unfortunately we're running out of time. And so I think the takeaway that potential impacts from AMOC collapse, just like impacts in general from climate change, are possibly severe, that we need to look at extremes, and also things like seasonal changes that might not be at the forefront of policymakers, and that we need to collaborate with people who understand the policy sphere and can act as knowledge brokers, like you just said, Laurie, is good takeaway. Thank you to both our speakers for your fantastic inputs and for the discussion. Thanks for everyone who attended. Thank you for those of you who asked questions. And yeah, I think there will be more events in this discussion series in the fall. They will be announced on the website. And with this, let's wrap up. I wish you all a nice afternoon.
Thanks,
Bye-bye.
everyone. Bye-bye.